Jó estét kívánok mindenki, nagyon szívesen és szeretettel köszöntünk Önöteket, és nagyon örülünk, hogy egy fiatal mérnök van itt, aki nekünk elő fog adni. És köszönjük szépen, hogy itt vagytok. A konzulátus fent van az első emeleten, ez a konzulátushoz tartozik az egész, hát ez az épület. Nem az egész, csak a része. Úgyhogy mindenkit szeretettel köszöntünk. Zoltán.
Köszönöm mindenkinek, hogy eljött. A Szilíciumvölgyi Innovátor Klub az egy politikamentes csoportra, és havonta szoktunk egy előadót kérni, hogy előadjon nekünk, és érdekes dolgokról beszélgessünk. Köszönöm mindenkinek, hogy idejött, és fogadjuk szeretettel Zsófi.
Welcome everybody. I'm going to be switching to English from now on. I'm Zsofia and tonight I'll be presenting to you about additive manufacturing. So a little bit about myself. I'm currently a senior at Purdue University, where I'm studying mechanical engineering. I'm interested in CAD, product design, and 3D printing. And also, I have interesting news. Just 2 days ago, I got the letter that I was recommended for admission to Berkeley University. Yeah, so I'll be doing a master's program there most likely. But this is what you're here for today. What is additive manufacturing? Well, when you want to create a part, you have one of three options. Either you can take material and form it into a new shape. You can take a chunk of raw material and cut parts away from it. Or you can create it using additive manufacturing and build it up layer by layer. Why should you care about additive manufacturing? Well, formative manufacturing processes take up a lot of space, and they need specialized equipment because they handle really hot materials most often, and they need powerful tools to be able to create parts. So you will not have access to those. Subtractive manufacturing processes are similar to that. Those can be scaled down a bit. So CNC machines and so those can fit in your garage, but you will have to dedicate your whole garage to it most likely if you want a good one. So that is also not for everybody. Additive manufacturing machines, on the other hand, they can be scaled down to such a size that they will fit on your table. And why would you want to have an additive manufacturing machine on your table? Well, let's say your screen handle door breaks. What can you do? The replacement parts that you find online are not to your liking. And in that case, you can either accept that or you can print one. Let's say you found the perfect pot to store your goose fat in, because they don't make that in America. And us Hungarians need our goose fat. Well, you can accept that it won't have a lid, or you can print one. And then maybe you want to make Hungary-shaped gingerbread, but nobody makes cookie cutters in that shape. You can either accept that, or you can print one. Additive manufacturing comes in 7 different types, but most of the machines will fall into one of 3 categories: fused deposition modeling, stereolithography, and selective laser sintering. FDM is the one that you're most likely to be familiar with because it's the most common and it's the easiest to get into. This is the one that you'll think of when somebody says 3D printing. This one mostly uses thermoplastics as raw material, but other filament types exist. However, it will usually create a rough surface finish. It only has a medium accuracy, and all the overhangs that you design into a part need to be supported or they won't come out correctly. Those support materials need to be trimmed away at the end. So that also adds to the post-processing. Fused deposition modeling works by taking the filament spool, heating it up, and pushing it to a nozzle where it is deposited into a specific point. Here in light blue, you can also see the support material. And there's an example of an FDL model part. You can see the layers in it. All the parts that you see in the table for those people who are in person, they were all created using FDM, but I like to call out 3 specific parts. This first one is a plating, which is donated to me by Purdue's Bechtel Center. So I do not know its story or its purpose, only that whoever created it abandoned it. So now it's mine. It was made of nylon, and it has carbon fiber strands woven into it. So it's way stronger than a regular FDM part, and it can even bend a little. The other 2 are actually my creations, so I'll tell those stories later on. But for now, you need to know that Chicken the Second is made out of ABS plastic, which is the stronger type of commercially available 3D printed filament. And the last one, Neil Headstrong, he's made out of PLA plastic, which is what the vast majority of FDM modeled parts will be made out of. This is the lighter, cheaper, more available filament type. The second type of additive manufacturing is serial lithography, which is a bit less common than FDM. That is because of the raw material that it uses. SLA works by taking liquid resin and cross-linking the polymers using a laser. You'll see that on the next slide. The unfortunate part is that this liquid resin is toxic in its raw form. Once you've fused it together, it's fine, but when it's in its liquid form, you should not touch it with your bare hands, and it also generates toxic fumes. The trade-off for this is that you can create beautiful, smooth, dimensionally accurate pieces. Those pieces still need to be supported, which is the spider web structures that you see on the screen, which do need to be removed at the end. So as I said previously, SLA is made by shining a laser to the underside of a transparent bag, which makes the resin solidify in a specific pattern. This layer of resin then sticks to this platform, which is then raised up slightly, and the process repeats again, and that's how the part is slowly risen out of the bag. You can see an example of an SLA printed part, and see just how tiny it is. That is somebody's finger, but there's still a lot of detail there. The 2 example parts I have with me, they were also doing it to me by Bechtel. This is a half turbine that failed, but they used it to show off just how accurate the process is. That one has ceramic particles mixed into the resin, so it feels a little bit like porcelain. This ring is partially made of wax, and they made it for some sort of event, but they have leftover pieces. Selective laser sintering is the cool one that I unfortunately couldn't get to try out yet, but I would love to one day. This is more complicated, and you'll really only find it in factories, industrial places, and university labs. Purdue has polymer making ones which work, and a metal making one which is locked away into some sort of basement because it's a massive health and safety violation. So I didn't get to see that one. Yeah. So these type of machines use fine powders, which can be made of either polymers or metals, which are hazardous materials due to just how small the particle sizes are. So it's not good if you inhale those. The parts that you get out will have a rough surface finish, but they will be highly accurate. And the reason I'm so excited about SLS is because polymer powder printing does not require supports. Whenever the part is printing, it will just sit on the unfused powder. And when it's done, you can just pull it out. Metals do need supports because they're heavier, but that's like a fair trade-off for being able to print with metals. SLS works by heating up the powder, spreading a thin coat of it over the build surface, and then shining a laser over it, which melts the already heated up powder together in specific places. After that, you roll a new coat of powder on top of it, and you fuse it together again with the laser. And this is the last part that was donated to me by Bechtel. Similarly to the plating, this one was also abandoned, so it's mine. And if you look closely at it, you will not see any layer lines like in FDM, but it will feel powdery. So now that you saw the 3 processes, how do you actually create those parts that you see? The first step of that process is to take your idea and turn it into a 3D model using something called a CAD software. CAD software stands for computer-aided design, and it comes in 2 main flavors. It can be parametric or freestyle. Parametric is when you want to make your part a specific dimension. So that is equation-driven, and that's the one used by engineers. Freestyle is for organic shapes, statues, figurines, and it's primarily used for artists. But nowadays, engineers also use it for surfacing. For parametric, you have programs like Autodesk Inventor, NX, CATIA, FreeCAD, SolidWorks, Creo Parametric, and my favorite, Onshape. For freestyle, you have Blender. Yeah, all right, you do have other alternatives, but usually it's going to be Blender. So once you have your part modeled, what do you do with it? You slice it. Slicing is a required step that usually gets left out of the discussion, but you have to do it because a CAD software cannot talk to a 3D printer directly. When you export your model from a CAD software, you'll get it in the form of an STL file, which describes your part in 3D space, but it doesn't tell your 3D printer anything. What the slicer does is takes this 3D object file and turns it into instructions for the printer to print it. An STL file is something that you can share with all of your friends, but G-codes will be specific to printers and specific to situations. So a G-code will be unique to your specific needs. Yeah. During slicing is when you set the parameters for your object, like density, layer height, printing temperature, whether you want supports, where you want your supports, and how you're going to try and stick your part to the build plate. Here you can see 2 parts. One of them is the Scout Lily. It is solid and it has straight walls, so it didn't require any supports. The other one is this poor semifloor statue that's still encased in its support tower. This is a 2/3 scale replica of the original, which was printed with water-soluble supports for a really good reason. So for CAD softwares, you have a ton of options. For slicing, you really only have Cura. Other variations exist, like Ultimate Cook Cura and Cura Luzbot, but really they're just the same program. Sometimes 3D printers will have their own specific software, but the vast majority of printers can be run off of Cura. So after you have your G-code, you load it into your printer and you start the process. The 2 parts that are currently going around are featured on screen. So at the center is the poor semifloor statue encased in supports, which would be really difficult to remove if I went at it. There is a risk that I would break the model. So that was why water-soluble supports were used on the original. The second one, the scalary, that was just printed with a simple skirt, which is this little, those little golden filaments at the side, these things. Those peel off pretty easily if you do it correctly. Because of the rough surface finish, you sometimes have to sand your part to make it more smooth. And then this is the original semiflora statue, which you can see with all of the supports removed. I sanded this one down, coated it in a primer, and painted it. So you see how the process is done. Now I'll tell you about some of the more interesting things I designed during my journey. I was introduced to CAD design in middle school, and it immediately captivated me because suddenly anything I could think of could be created and made. So any little statues I thought of, any characters I wanted, or my very first part, which was this medal. I still have it today. So I designed this myself during my freshman year in high school, where I joined the Project Lead the Way program. And that's where I really got to figure out that I wanted to be an engineer. That program taught me a lot of introductory information about engineering, different fields, and one of the semesters was specifically focused on CAD design. So I took the opportunity and designed something for myself. It's a pretty basic model, but I was really proud of it at the time. And I'm still am because it's beautiful. Although that was the first print that I designed, it was not the first part that I personally printed. That was this one. This was how I learned that 3D printers cannot print in the air. They need supports underneath it, or the bottom parts will turn into spaghetti and look all weird. On one side, you can see the original CAD model, and on the other, you can see the result. Now, you can see the outer ring. It's supposed to be a circle, but it's actually, in the final print, a 17-sided shape. Well, the reason for that is units. I learned a valuable lesson with this one. In America, engineers have to use two systems of measurements, imperial and metric. Slicers will always think that your STL file is in millimeters, unless stated otherwise. And I knew this, but I didn't know how the export function worked. And I originally set this file up in the imperial units by mistake. I meant to set it up in millimeters, but it interpreted everything in inches. So when I exported it, I set the setting to inches, and that meant that the program thought that the model was in millimeters and converted everything to inches, which turned the part into a really tiny little resolution. Hence why the circle is not a circle. Right around the time I redesigned the pendant, I got my very first 3D printer, which was this tiny little beginner's machine. It was adorable. I loved it. It also printed really loudly. So yeah, it had a really loud singing voice, but it was also mesmerizing to look at. The first print after that cat in the middle of the table, that's the test print that they send out with the printer, was of course my star pendant. I tried to scale it down and set it up again, this time knowing that you have to use supports. And yeah, I got some varying levels of success. The only problem with my printer was the absolutely tiny build surface. It was a 10 centimeter by 10 centimeter area, which is actually really small if you get into printing. So I had to split my parts up into multiple pieces for them to fit on the build surface, and I had to design joints into them. On one picture, you can see a flute that I attempted to print, which had to be printed in 2 parts because it was too tall to fit into the build area. On the other side, you see several things that were in different pieces, like the prototype Christmas tree, which is lit up in the center of the table, and a decorative stylus box that I tried to design for my pen. Unfortunately, I couldn't find that one. That one got lost. The part where this came back to bite me was with Chicken the Dragon. Last year, I took a fluid mechanics laboratory course where our final project was to come up with a question that could be answered with the tools and techniques that we learned during the laboratory. We had to design an experiment to carry out, and of course, do a report at the end, because it was a college course. So my team decided to design a drag experiment in one of these wind tunnels. Purdue has 2 of these for undergraduate use, and we're really proud of them, because allegedly we're the only institution in the country who does that. So I proposed that we find out just how unviable it is for a dragon to have a long tail due to the additional aerodynamic drag it would generate. To answer that question, I designed Chicken, who got his name because he kind of resembles a rotisserie chicken. Yeah. He has 3 separate tail attachments, which is the nubtail, the taper tail, and the fin tail. And our experiment was to compare the fin tail and the taper tail to the nubtail to see just how much drag they add to the model. Well, Chicken the First was printed in several different parts and then glued together partially for 2 different reasons. The first one was that we thought that we could only access the chest chamber through this tiny little porthole, which is about the size of my hand. For those of you here in the room, you can see that Chicken has a way bigger wingspan, so he would have never fit through that hole. Later on, it turned out that actually the roof of the test chamber could be removed. We just didn't know that because we were never allowed to touch that part of the wind tunnel. But yeah, fortunately, that was a feature. The second reason was because he would not have fit on my printer in one piece. An unfortunate side effect of that was that the main body and these little pegs that held the wings on the body during the experiment were printed in such an orientation that the layers ran parallel to the weakest part of the peg. Well, the thing about FDM parts is that they are prone to delamination, and they break really easily along the layers. In other directions, they are strong, but in that specific way, if you apply a force, they will fall apart. And that's exactly what happened to Chicken the First. We cranked up the wind speed to 40 miles per hour, and all of a sudden we hear a bang. One of the wings just sheared right off, and it collided with the netting at the end. That netting is there because if anything flies back into the turbine at the end, that damages the wind tunnel. So that was a pretty scary incident. Thankfully, all of the pieces were stuck against the net. The little pegs that sheared off were actually stuck inside their holes, so nothing went in. But that was pretty scary. Also, we were down our experiment model, so we had to call it short for the day. What we did was go around campus, find the largest printer that was there. It was a huge 1 foot by 1 foot build area. Rotate Chicken 45 degrees so he actually fit there, and print him in one piece. We also picked ABS plastic for the material to just make sure that it cannot come apart. So yeah, as you can see, Chicken the Second survived the wind tunnel experiments, and he's still here with us today. For anybody wondering for the outcome, the fin tail actually generates the least amount of drag. So no, it is not aerodynamically infeasible for a dragon to have a long tail, as long as it has a flared attachment at the end. It loaded, yay. So another fun project I did, this one was last semester for my toy design class. The end of semester project was to create a mechanical toy. And I was responsible for designing the upper third of this rocket, which has all the moving parts inside of it. Something you have to know about Purdue is that it's also known as the cradle of astronauts, because a lot of our graduates went to space. One of them was Neil Armstrong. So yeah, he went to Purdue. That's why this little astronaut is named Neil Headstrong, because my team decided to go with a pun. We created a toy called a useless box, which turns itself off when you flip the switch to turn it on. So in this case, we had it in a loop. The switch was always flipped. And when you flip the switch, one of the servos activated to open up the roof, and the second servo activated to let Neil Headstrong come out and turn the box off. He's headstrong because he does not want to go to space. He will keep terminating the launch sequence. But this story is not about him. It's about the little golden part right in the back. That part exists because the rocket's nose cone failed it during printing in an epic way. So here you have a high-resolution model of the rocket cone in a slicer. You can see this little part that hangs down. That's the attachment where the linkage arm connects the top to the servo that moves it. So it's a really important part. Without that, there is no attachment and there is no movement, and the toy is non-operational. Also, it's an overhang, so it needs to be supported. So when I went to slice it, I put a support tower there. And the only printer I could secure was a really old, what was it? Task Pro? Yeah, that's what it was. It's a huge printer, really robust, really good dimensional accuracy, but slow, painfully so. And this is a big part. So printing it took 18 hours. That is on the higher end of printing things. Usually you can get away with 6 hours if you're going for smaller things, 2 hours if you have a small printer, if you have a fast printer and a small piece, 10 hours if you're printing many things. 18 is a lot. So I thought I'd just come back tomorrow to the printing lab and receive my finished rocket cone. But that was not to be the case because the support tower didn't generate properly. Instead of being under the handle, it was right over there for some reason. I'm still not completely sure how it happened, but it was rotated 45 degrees around some random axle and also attached to the wrong surface. So it wasn't supporting the critical handle. And of course, when I turned the part over, the most important part was spaghetti. Not something you want to see after an 18-hour print, especially not with a looming deadline. So yeah, our part was due to be presented in like 2 days. We can really reprint it. So the way we solved it was that my teammates took the spaghetti and cut it off, sanded the remainder of the handle that was still there. And I went into the CAD file, isolated the part of the handle, and printed that separately. We then grafted the handle back onto the part, and that worked. So Here you saw what I used additive manufacturing for. Toys, jewelry, little trinkets, science experiments. But the technology has so much more potential than that. It can be used to revolutionize the human organs. So a lot of people are on organ transplant wait lists, and a lot of people die on those wait lists because they cannot find a donor. They cannot find a match. Or even if they do find a match, their body rejects the organs. A team at Stanford University is currently working on a technology to 3D print a heart out of stem cells. Your own stem cells that your body recognizes as your own organs and doesn't reject. If they can get this technology to be commercially viable, that would save a lot of lives. So let's root for them. Another really popular application of the technology is prosthetics, especially prosthetic hands for children. Children grow a lot, so they need their prosthetics replaced often, which can get really expensive if you manufacture the prosthetics with traditional methods. It's also not easy to manufacture them with traditional methods because they need to be customized really much to the children. Additive manufacturing, however, is made for that. It's really easy to scale, customize, change, adapt, and even make it pretty. So yeah, this is a really good application of the technology. A more surprising application is in the aerospace industry for airplane parts. This is where SLS comes in and why it's so interesting. The top wing bracket is manufactured using traditional methods, and the bottom one is made with SLS printing. Now, the bottom one uses a lot less materials, and it's also about half the weight, which is really important in airplanes. However, these parts have the equivalent strength, so they are just as strong. The bottom part cannot be made with traditional methods because you cannot create a mold that you could cast this in, and you can't really machine it either because of all the little turns and holes. But the vast majority of material is not doing anything in the top bracket. So the bottom bracket removes all the unnecessary weight, and this could help airplanes save fuel in the future. A relatively recent application is chocolate. This technology is pretty new, so only vase move printing works, which is where a printer goes around on one spiral and keeps building on top of that. It won't take the place of everything that currently exists. Like with chicken the first, it has a really directional strength. So it will come apart along the layers, especially with FDM. SLS parts are way more porous than cast parts, so that also impacts their strength, which is a concern in some applications. Anything that you want to print with also has to have a melting point. Otherwise, you can't really form it into a new shape. So that limits materials. And it's also, on a high scale of production, it is lower than most traditional production lines, and therefore more expensive. So the big factors are going to stay. Where it really shines is unique, one-of-a-kind parts and rapid prototyping. things that need to be customized, changed, and adapted quickly. But it's not really good for something that you create a million parts of. You also have a rough surface finish in 2 out of the 3 cases, particularly FDM and SLS. Resin printing doesn't have this problem, but that one has other issues, namely the raw material being poisonous. So there's a lot of post-processing you need to do. That is also one of the other reasons why large flow lines will not adapt to 3D printing. Some of the other aspects that have to be considered are copyright. Technically, people who are tech savvy can take video game characters, rip their models out of the video games, and put them on a 3D printer, and voila, they have a figurine of the video game character, which they shouldn't have. You could also technically print any piece of Legos if you have some engineering skills, a caliper, and the specific Lego piece, which Lego will not be happy with you if you do that. There's also the environmental safety things. So that's mostly for SLA with the toxic material. You have to cure all of your resin before you deposit it, and you have to bring it to a hazardous material collection facility. And food safety. This is for FDM parts. So the ones that have visible layer heights. Bacteria can get into between the layers, and it becomes really difficult to clean. So you shouldn't store food inside the containers. You can use it as a lid or a cookie cutter, that's fine, because it's not in contact with the food constantly, but you shouldn't use it as a replacement for Tupperware. And then finally, the part that you've been waiting for. You've been hearing about this technology, you've been seeing what I did, you've been seeing what it can do otherwise. How do you get started? Well, the first step is to learn how to model your ideas. Pick your favorite CAD program, sit down with it, and learn all of the functionalities. They're really neat things. I would personally recommend Onshape at first for beginners because it's a really nice, user-friendly program. If you think of all the heavier, more beefier CAD programs like Creo and SolidWorks, those are like Excel. Onshape is a lot more like Google Sheets. It is browser-based, lighter. It doesn't have all of the functionalities of the bigger programs, but it will have all of the things you need if you're just designing things for yourself at home. It's also free, if you don't mind the whole internet being able to see your models. Yeah, student versions are allowed to create private documents, and paid versions can do that too. But if you go in with a free subscription, then everybody can search up your models that you create. This will generally not be a problem if you're just designing things at home. And also it can be circumvented by giving the files Hungarian names. Or maybe you don't even have to learn how to model, because sites exist that will give you STL files either for free or for some money. Things like Thingiverse, Minifactory, Pinshape, and in some cases GrabCAD, though that is more of a CAD model sharing site. You can go here and pick all of your favorite files and download them and print them at home. But if you want to learn how to create your own things, or I don't know, replace your door handle, those you'll probably not find files like that on the internet. So that would be a reason to learn the CAD programming. Next, you have your model. You want to print it on something. Now, printers are becoming more advanced and cheaper at the same time. So it's not too big of an investment to get one. 4 years ago, when I got my first printer, it was about $100. But now when I got my second printer around Thanksgiving, it was $200 and way more advanced. So this printer has 2 support columns instead of just the one, which improves accuracy. It has 4 times the build area, so I no longer have to design junctures into my parts. It's still not enough to print chicken a second, but a 90% scale model would fit on there. Yeah. Filament is also not too terribly expensive. A standard roll comes between $10 to $15. Fancy ones can get more expensive, $30 to $40. This is for multicolored filament, golden filament, really high quality filament, or packs of filament. And the next step is to learn to slice. This step you'll have to do even if you grab your models from online and don't design them yourself, because this is where you determine how you want to print your models. If you have a 3D printer at home, you have to do this step by yourself. And then most importantly, keep experimenting. You'll get the best results from additive manufacturing if you know your printer and know your filament really well. Sometimes you'll have to run multiple runs to get the results you desire. People often run calibration prints too. So sometimes you can just get lucky, find the correct settings, and your product will come out perfectly, exactly as you imagined it. But sometimes you have to tweak the designs. And then sometimes your printer just has a bad day, and no matter what you do, it will probably present you with a bowl of spaghetti instead of the part you wanted. But yeah, the important thing is to not give up, keep experimenting, keep trying new things. And thank you. Yeah, any questions?
We had a question from online whether if it is possible to print sideways or upside down with some kind of rotating head or something, so you wouldn't need to be just depositing the same layers.
Oh, that's multi-axis printers. They might exist. I don't know of many that do. Let's see. This printer is a 3-axis printer, so it can go in the X, Y, and Z directions. A printer head that could rotate would be a 5 or a 6-axis one. Yeah, I haven't seen them commercially, but they will probably exist in the future, and they might already exist. The biggest challenge is to keep the filament from breaking while you're rotating the print head, because if you bend it too much, it will snap. The filament is a little bit brittle under some conditions.
Are you aware of any automated software that could do the slicing by itself?
Do I know of any automated software that can do the slicing by itself? One of my university professors is apparently working on one of those. So she's trying to develop AI that could help with your workflow. Currently, I don't know of any that exist, but normally you would want to do the slicing by yourself because you want to get layer height, infill density. It's just a few panels and values that you write in currently, so it's not exactly hard. the program creates the G code by itself based on these values and the 3D model that you put in.
What will you be doing at Berkeley?
What will I be doing at Berkeley? So I chose the product design branch. So something with that. Yeah. Yes.
Can you explain what these are?
Oh, yeah. So these are captive link parts. They are my newest obsession.
Why?
It's because you can print them in one piece and they will move. There are 2 out there that are already broken. The rest of them are still in one piece. You have to apply a little bit of force right here in the back. You have to do it carefully, and you have to rotate it over several times. There's a chance that you will break the middle part, but oh no.
He didn't. He did it.
Yeah, like that. So you can just take this. This is a static part, but you can turn it into a moving part. This is something that you can't really do with traditional manufacturing because, well, with an advanced CNC, you can't reach in there and carve it. But you would need a 5-axis CNC for that one. And most of them are 3-axis. Yeah, so right here. 3D printers can't, so they cannot print into the air, just overhangs, just hang out over the void, but they can print with little air gaps. And that's what this piece is taking advantage of. The way I set it up, there's a, what was it? A 2.4 millimeter air gap between both points of contact. And I printed it with a 1.2 layer height setting. So it skipped 2 layers when it went from the middle surface to the bottom of the top surface. And that gives it enough room for it to be able to move eventually.
Can I print on ice? Can I print on ice?
Ice?
So that it would matter the as a support.
I don't know of anybody who tried. You'd have to secure the ice down. Or no, it would get in the way of the print head. So supports are something that you build up alongside your print because the print heads are usually really bulky. That goes for FDM. SLA and SLS, the other 2 techniques use light. So that one is not, those ones don't have a print head that could knock your support over. But those things could get blocked by the support if you have any there.
You mentioned dissolvable supports. How does that work?
Dissolvable, oh, I mentioned dissolvable supports. Yeah, that was all the way back with the semiflora statue. It's going to take a while to scroll back. Right there. So some FDM printers have 2 print heads. Most of them have only 1, but some of them come with 2. So that is how you get multicolored print, and that is how you can print with dissolvable support. One print head prints the black PLA filament, which makes up the statue. The other print head prints up the other type of water-dissolvable filament. And that's how you get dissolvable supports.
Out of all these methods that you went through, do you know which one is the most heavily researched one? If there is like one that is more popular than that,
Which one is the most popular of the three methods?
in terms of research.
In terms of, I don't know about research. SLA is the oldest. FDM is the one that's most available to the average person. And SLS is the coolest one. But that one, yeah, that's going to be in the basement of your college if it's not locked inside the cabinet, like it is at Purdue. Yeah. If we have time, I can do a show and tell of all of the pieces that I brought. Okay. This one was another product of toy design. So the same class that I did, Neil Headstrong for. So this was an earlier exercise during the semester. This was about tolerancing. The exercise did say to design a fidget spinner that could fit 2 to 4 of these nuts and a bearing inside of it. And we were told to print to tolerance it for multiple sizes, so that we could see what was a clearance fit, what was an interference fit, what was a transition fit for 3D printers. So when we went to print more parts throughout the course of the semester, we knew exactly how big we had to make them.
What is a transition fit?
It's halfway between a clearance and the interference fit. Question was, what is a transition fit? So yeah, sometimes the parts will be in interference with each other. Sometimes they will be in clearance, depending on how big they actually are. Okay, yeah, this one is a cool one. This is a Mars rover claw. This is for my freshman year in college, for first year engineering. So we were tasked with creating 2 autonomous robots during the year. I can't remember if this one was the first one or the second one. It was your standard line following robot, but the story was that we're in a Mars base and the Martian sand covers the track at some places, and you have to design a robot that can follow the dotted line, follow the striped line, follow the solid line. Nobody could follow the dots. That was a given. But yeah, the other task was to grab 3 8 packages that were different shapes. One of them was a cone, one of them was a square, and the third one was a cylinder. Actually, I do have a good picture of the rover claw, but it's right there. Oh, you can't see it. Yeah, what you have to look at is the inside surface. So this inside surface is perfectly designed to grab all 3 of the crates. And then these little parts are interfaces for Lego parts, where you could stick the axle in and the motor would drive it. And the 2 halves of the mandibles are coupled together with gears. Now, this was my first introduction to involute gears and just how complicated they are. I went in there I went onto the internet thinking, how hard could it be to design an involute gear? I pretty quickly realized it was really hard. I spent an entire afternoon researching it, and then I ended up eyeballing it. Yeah, but it works well enough, and it was good for a freshman project. I don't have a picture of that, unfortunately, but 2 years later, I went back, and that time I found the formulas for metric involute gears. So during my junior year, in one of my other classes, we were told to design the world's most inefficient fan. It was supposed to be the world's most efficient turbine, but we ran it in reverse, so it was the world's most inefficient fan. We powered it on one end. We had a massive gear train in the middle, and we had a fan at the end that depended on your TA, whether it actually had to spin or whether it could just be there. So, yeah, our professor wanted that to spin because she said that if it didn't spin, that's a civil engineering project, and we were mechanical engineers. Somebody did an insane sun gear, multi-level sun gear contraption. That one, you had to rotate it like several million times for the last gear to move one peg over. And that guy showed it to the professor, and she was like, "Congratulations on your civil engineering object." She wasn't happy about that. Ours actually moved. So we fulfilled that requirement too, but in a pretty scuffed way. Oh. I wonder if I can pull it up. It's a bit complicated because my computer split three-way between the meeting and the projection. Yeah, I was going to print those gears too, but I didn't have time for it.
I have a question. So sometimes you mention you created something, and sometimes you say, we did it with my team. Which one is easier when it comes to engineering a 3D printing or a part or a cloth? Is it easier to work in teams with engineers or by yourself?
When you're working with teams and engineers, usually you designate a CAD person and they do all of the modeling. Or if there's a lot of modeling to be done, you split it between several people. CAD softwares are, with the exception of some packages that let you share projects, and Onshape, which is it's the Google suite of CAD programs. That is the only one that is well connected to the internet and actually lets you share with your teammates. So sharing parts is kind of complicated between people. So you usually split up the work or designate a single person to do it. And that's usually the jobs I take on because I love doing that.
On a retail level, I mean, some of those printers are $100, $200, right? I imagine that lots of kids are doing this in their garage. So if I want to do it, I order one and I order some resin off the internet. Or how do I proceed?
Oh, yeah. SLA printers are a lot more expensive. So how do you proceed if you want to order something off of the internet? You order something off of the internet. Yeah.
But it's
How do
not
I
very
know what to
hard.
order?
Not very hard.
Yeah, you ask for recommendations from friends and from online review places.
Okay.
Yeah. I'm not familiar with the resin printing side of things. I know some things about FDM.
Pretty much like the same type of problem. If you are a college student and you purchase your first car, doesn't matter what kind of car you purchase, because a year later is going to be like sold or like taken apart or something. So just start out with something.
Right. I only remember the resin, but I know the point of view.
I like the connect.
Yeah, pretty much. That's a good answer.
So could someone turn wood into liquid form and
Oh, yes. There's been a recent development. Wood-infused filament now exists. but it scratches up the inside of the 3D printer. So it's still a work in progress.
So it's mostly plastic
Yeah, it's mostly thermoplastics and chocolate.
and chocolate.
What about ceramics? I remember this was many years ago, there was an online 3D printing shop and I could upload a model and they printed it out in ceramics, but I haven't seen that.
Ceramics was possibly resin printing.
It was printed in clay and then they did the traditional firing and then that's how they made the ceramics work.
So a clay infused filament.
Something like that, I don't know exactly.
Yeah, that probably exists too.
Oh, cool.
I can imagine. Because that would be like, that one would be in the form of a putty. Yeah, it would be difficult to keep it in one shape during the printing process, but I imagine it could be solved.
How much should I expect to pay for a metal powder laser sintering setup?
I don't know. That's expensive. Those are really big machines. And the raw material is also not cheap.
You know, it's one of those things where the list price is contact us.
Exactly.
Yeah, market price. Thank you very much.
Thank you very
This was very good.